email list, and I had for a while, but it appears that somehow you got chopped off.
I don't know. I think the migration to Outlook or
Yeah, it has been hard. It has been hard.
whatever migration they did it during finals week, which was also not great.
No. It was difficult. Yeah. Okay. How are we doing? Yeah. Okay. Today I'm making a little bit of a, let's see. Okay. All right. Hi, Sunny. Hi, Dr. Mahanti.
Hello, Surajit. Good morning.
How are you? Good morning.
Good morning.
Sorry for the noticeable change.
What happened to your hair?
I just cut it. I couldn't get that long hair.
I have never seen you in this format.
This is the first time in my life, actually.
It's good. It's good. You're looking like a monk.
That's what my friend told me. Yeah.
You're looking like, I mean, you usually have like long hair, like it's
Yeah. Last week I had long hair.
Hey, that's good. Overnight change.
I mean, Sunny had long hair when he was our student. Over the years, I've known him, which is more than 20 years. It's shocking, actually. No, you're looking good.
Thank you.
Hey, Hema. Hi, Yuman. Good to see you. All right, so Ryan, you want to try out sharing your screen? Okay. Oops. What happened? Okay, great. All right, now let's come out of the screen because, okay, hang on. View options.
Stop sharing.
Yeah, let's stop sharing because I think, 1 second. Hopefully,
It's 11 o'clock.
Hopefully I've let everybody in. Seems like it is a little tricky to let people in when you're screen sharing and stuff. 1 second.
Is Buffalo getting a heat wave, Surajit?
It's very nice, actually. It was hot last week, but it's beautiful out. It's like probably not even 70.
Yeah, we're just checking. Is in the west is going to be 120, 110, 70.
Oh my God. And how is it in Michigan?
Michigan is beautiful. It's 80, 75, 80. It was hot, but it's cooled down.
Okay. Yeah, here also I think it's been hot and it has calmed down quite a bit. Since it's 11 o'clock, I think there are some more people joining, at least that's what they told me, but we might get started. Yeah, let's get started because, okay. Hi, Pragya. Okay, there we go. But let me first introduce you. Oh, Joseph has joined. Okay, first. I don't want to start introducing you and have to admit people. Hey, Chris. This is better. Okay, should I start introducing you?
Whenever you're ready.
Let's go for it. Okay, so today's speaker is how studying ants helps us build better robots. I'm so happy to introduce my colleague, Professor Ryan St Pierre. Ryan is a Ryan has just joined as an assistant professor in the Department of Mechanical and Aerospace Engineering at Buffalo. And he and I got to know each other for the past quite a few months, and it's been a really exciting set of meetings to have the chance to talk to him and set up some new work with Ryan. I won't read the abstract, but let me say a few words about Ryan. Ryan did his doctoral work at the University of Maryland with a research focus on small-scale locomotion and finished his degree in 2018. He got a BS and MS from Northeastern University in Boston in 2013. And his research interests include microsystems, robotics, and organismal biology to understand highly dynamic biological systems and create microbot analogs, all at small size scales. His work is on microrobotics and has been recognized with the Best Paper Award at the 2018 Solid State Sensors, Actuators, and Microsystems Workshop, and covered by IEEE Spectrum, which is a well-known publication. Recently, Dr. St. Pierre has been highlighted on the 2020 Forbes 30 under 30 science list, and is presently an assistant professor, as I said, at the Mechanical and Aerospace Engineering Department at Buffalo. So Ryan, it's all yours, and thank you for joining us.
All right, well, thank you for having me. So I'm going to talk a lot about ants today, and I realize this is probably going to be a bit different than normal for this seminar series, but
Which is great.
Interesting. So I just joined Buffalo this January, and I'm starting up my lab, and my lab is called the Robot Form and Function Lab, where we look at this relationship between design and control. And it really takes inspiration from the field of functional morphology, where we look at what the apparatus on an animal looks like and how do we infer form and function and that relationship. And so my group has a lot of contributions to robotics, microsystems, and a lot of insect biomechanics. And so I do often have to make that distinction that it's insect biomechanics and not human biomechanics, because arthropods are very different, and I hope to show you how they are different and in all these exciting ways. So I am particularly inspired by ants, and I think ants are amazing, and they do incredible behaviors in a diversity of terrains. They can run quickly, they can carry high loads relative to their body mass, and they have all sorts of interesting behaviors, and they exist on almost every continent besides Antarctica. And I think that that's just particularly inspiring for someone who works on microrobots. But microrobots have not even achieved what ants can achieve. And so that means there's a lot of work to do in basic science and engineering in order to get small scale robots that act just like ants. And so today I really want to talk about the striking behavior of ants. And to start, I'm going to talk about this one species of ant, which is called the Dracula ant. And Dracula ants are named that because they participate in a carnivorous behavior. They drink the hemolymph of other ants. But we'll start here, and we'll start with the striking behavior of the ants. And playing this movie, you see how the ants touch the two tips of its mandible together, and then they slide past each other, kind of like how we snap our fingers. And so that is this really interesting striking behavior. And what we find is that this striking behavior of the ants and the jumping of this flea and the snap of a shrimp, this is a snapping shrimp that cavitates water, and even the closing of a Venus flytrap can all be unified under the same set of fundamental dynamics. And so us as roboticists, we're really used to this idea of direct actuation, where we have a motor connected to a mechanism, and the motor is doing the work to move that mechanism or move that mass. And that is really what we think of as humans as well. We have our muscles connected to our bones, so that makes these lever systems, and that is the direct actuation. But all of those examples that I showed you of the striking, the jumping, the plant actuation, that is all unified under the set of latch-mediated spring actuation. And what's interesting here is instead of using a motor to directly power your movement, what you do is you use a motor that is modified to load a spring. And so it may take, it's this, generally in arthropods, it's a force modified muscle. So you load a lot of force over a very long time into a spring, and then you unlatch it, and the recoil of the spring is what drives this motion. So it's no longer directly actuated, and instead you're actuated by a spring. So you're using a spring as an actuator. And that gives you a lot of these just functional trade-offs in how do you do design and control in robotic systems, and what are your trade-offs in biology as well. And so to start, we really want to talk about, well, historically, we thought about how this latch-mediated spring actuation system has latches, and latches would just act as a switch. They're either on or they're off. So they're blocking the movement or they're allowing the movement to be free. And for us as engineers that want to make highly dynamic robots, we want our latches to disappear instantaneously, because that way we're not losing anything, losing any energy or losing any motion to the latch itself. But upon further investigation of a lot of these systems, we actually find that latch contributes towards the dynamics. And so switching over from this very sharp latch that has this, 90-degree angle to a more rounded latch, and we zoom in on the dynamics and we zoom in on that interaction, we now bring up this new behavior of unlatching, which is a rich area for study in all of these organismal systems, and it's a rich area for study in these robotic systems. And so what we do when we look at this, and if we look at this in the context of that LAMSA framework, that latch-mediated spring actuation framework, over here we are loading all of our potential energy into the spring using our very slow motor or our very slow muscle. And then during unlatching, that latch is sliding out of the way, and we get this transformation of potential energy to kinetic energy. And we find that we have this latch delay. So we have, how long it takes to unlatch the system to get to that ballistic motion that we're after. And we see these increased radii in biological systems in this Dracula ant. But when we look through all of the engineering work and look through all of the jumping robots and other impulsive and high acceleration systems, we see all of these sharp latches, but we don't see these sharp latches that instantaneously remove in biological systems. And so for me, who has masqueraded as a biologist during my postdoc, I want to know why. So why is biology not doing this, optimized performance? Why are we not always getting the most energy out of our system as quickly as possible as we are doing in engineering? So what are the trade-offs here, and what are we giving up? What are we accommodating for? And so that allows us to explore this behavior. So if we make a very, very simplistic model of this latch-mediated spring-actuated system, we have a spring and a mass and a latch with a radius that is pulled out of the way at some velocity. And we have some equations that describe the behavior. And I do want to note that this latch is infinitely stiff. And so the latch is kinematically coupled to the mass, and there is not a force being exerted from the spring mass onto the latch that would move it out of the way. So we're looking at this most limiting kinematic case. And so what we can find is if we solve these equations and we solve it for what we want, and we can mix things around, we can find this latch threshold velocity. And this latch threshold velocity relates our geometric parameters of our latches to a compression in the spring and some of our system parameters of the spring and the mass as well. And if we take the time delay, so if we take the time delay as that approaches 0, then we get that expression returned. And now we have an idea about how design, control, and system parameters all relate to performance. And that is very exciting as an engineer. And so, you know, when we have this delayed latch, so we have our, so this allows us to look at this system with a rounded system, and we can pull our latch out of the way. And if we pull it with a threshold velocity that is less than if we pull with velocity less than our threshold velocity, we can get a delayed latch behavior. But if we pull it with a velocity greater than our threshold velocity, then our rounded latch acts just like our sharp latch. And so we can get this diversity of behaviors out of a system where we thought we would lose energy. And so when we take these ideas and take these principles and put this onto this design map, here on the horizontal axis, we have the latch radius, which gives us our design parameter. And on the vertical axis, we have our latch velocity. So this is our latch removal velocity, and this would be our control parameter. And this dotted horizontal line is just representative of that latch threshold velocity. And so when we're below this dotted threshold line, we have a delayed latch, which means we can get this really big diversity of behaviors, and we can have our system take off with very low takeoff velocities, or we can try to, or as we move up and increase our latch velocity, we can get this instantaneous behavior. And so that is really exciting for me as someone who does micro robotics, and I want to pack as much as I can into a really small package. But we also wanted to test this principle using a very, very simplistic physical model. And so what we did was we laser cut a bunch of latches with all of these different radii, and we made a spring mass system, and we really confined it to this 1D motion that was, you know, indicative of our modeling. And we tested it to see how it worked, and we found the same behaviors in our model. And so we're able to, you know, use either this latch geometry, this combination of latch geometry and this combination of latch removal as this idea for control. And so we can use those two parameters in conjunction with each other to get a latch delay. And so we're able to really define our behaviors based upon our design and our control. And so that allows us to get a multitude of behaviors in our robotic systems. And so I started with the Dracula ant as this, you know, snapping behavior. And we noticed that the Dracula ant has these rounded mandibles. And so can we take our same modeling approach and our same, and sorry, my cat is on my desk and he's just being in the way. Can we take our same modeling approach and our same ideas and investigation and apply these and look at the biology and see if we can see some of these same physical principles? And so what we're fortunate with these Dracula ants is there's two major castes. And so there's a major ant and there's a minor ant, and they are functionally similar. They're just very different in size. And so what we can do is actually make a lot of assumptions about, you know, how these systems scale. So how does this latch scale? How does the spring constant in these mandibles scale? And what we can find is if we take some of these assumptions and we look at that in terms of the latch threshold, we find that that latch threshold is scale invariant. So whether you are a major ant or a minor ant, you have the same threshold velocity that will get you that instantaneous behavior. So that means that if you are below that threshold velocity, then ants should show a correlation between input and output. And if you are above the threshold velocity, then you don't see a correlation between input and output. And so that is exactly what we see with these two castes of ants. So these minor ant species, which are minor ants of the Dracula ants, which are smaller than the major ants, they all release their latch. So they have these two mandibles. They release their latch at a very high velocity, and their strike velocity and their latch release velocity is not correlated at all, versus the major ants, which can tune their latch release velocity, which tunes their strike velocity. And so this gives us an idea about, how are these fundamental principles of latch-mediated spring actuation seen in biological systems? And so it allows us to, tune some of these behaviors. And, so we've looked at this in physics, or, this very simplified mathematical model, and we've looked at it in biology. And me as a roboticist, I like to also look at this in terms of robots. And so what we want to do is take this really, really abstract form of the LAMSA model and then build up to a robot system. So we have that latch moving out of the way from a spring. And so going from left to right, we build up from this abstraction into these robotic systems. And all the way on the right is a robot that we made in the lab. And any good robot has googly eyes, in my opinion. And, what I really want to emphasize here is that we're using this latch as this control tool. So what happens in this latch-mediated spring actuation phase is really what's setting the final behavior in our system. And so what we can do is use how the latch is removed by that motor, and we can change the input to the motor, which changes the velocity, which will ultimately dictate the jump height. And so here is a slow-mo video of that same robot. And we set it at this low voltage, which would mean a low latch release velocity. And we get a smaller jump. And then we set it on a high voltage, which means a high latch release velocity, and we get a much bigger jump. And so this has allowed us to bake into our design this idea of control through the same mechanisms, which has allowed us to really pack in a lot into these small scale or resource constrained robots. So we don't need another set of motor or another set of actuators in order to do this controlled jumping behavior. We're modulating our jumping behavior from the mechanism itself. And so this is really, really exciting to me as someone who tries to engineer ants. And so really the biggest takeaway of this first part is that the geometry and the latch removal are pathways to control in these high acceleration systems. Since we're giving up this direct feedback control by using a spring as the actuator and not using a muscle as the actuator, we have to find out how we can embed control through mechanisms themselves. And some of the next things that I'm doing is looking at integrating real actuator dynamics, which is, we know that motors do not pull with infinite force, especially as you shrink motors down. And so there are going to be these new trade-offs with integrating actuators and mechanisms in terms of these robots. And so now I want to move into talking about this other set of striking behaviors. And so we first talked about the Dracula ant, which pushes its two mandibles together as this finger snap. And now this is a trapjaw ant, species Odonomachus, which moves its two mandibles from this horizontal configuration. And then you will see that it closes its two mandibles. And this is filmed at 300,000 frames per second. So this takes place, over in less than 1 millisecond. And these mandibles themselves are, millimeters long. So this is a very fast and a very small movement. And, looking at this movement in relation to other high acceleration and low mass movements, the trapjaw ant exists at this border of repeated use. So any of these ones with the X crossed out are actually just one-time use only. So it's this kind of this limit of acceleration and mass. And this is really, really interesting to building small robots and also small actuators that we want to be high force or high acceleration, repeated use. And so how do we do that? What can we learn from how the trapjaw ant closes its mandibles and bring that into the engineering world? So this is the study species for that. This is the Odonomachus. The species isn't known, but the genus is Odonomachus, and it's a pretty sizable ant. Its mandibles are, a little over 1 millimeter long. And when we dissect it, we have the mandible, and attached to it is the apodeme. The apodeme is the arthropod equivalent of tendon. So it's a stretchy strap, if you will. And connected to that are these big muscle fibers that pull on the apodeme. And so these species are incapable of an incredible diversity of behaviors using their mandibles. So this is that trapjaw ant striking this really soft-bodied grub. And so you can see it repeatedly doing that, and it's using its antenna to manipulate the prey. And so it's striking a very soft surface. And we can also see these same species of ants striking these beetles. And so you'll see that it actually strikes the shell of the beetle and it kind of goes flying because there's just a huge amount of force that needs to be put somewhere. And these species are also capable of using their mandibles to jump. And so this ant is being dropped on its face and it's using its mandible to snap at the ground and jump and recoil. And they're also able to use that same jumping behavior in granular media to get away from one of their natural predators, the antlion. So it's falling down this sort of conical pit, and right in the center is its predator. But it's going to snap at the surface of the sand to try to jump away and escape. And generally, it's pretty good at that. But in addition to doing all of these snapping behaviors and trapjaw behaviors, it can also use its mandible as this multi-degree of freedom multi-tool. So in addition to just closing in this nice, in this nice way, it can also use its mandible to manipulate prey items and interact with the environment. And this gets us thinking about, well, how can this one specialized behavior, so how can we get to this mandible that is capable of this precise circular rotation? And we'll talk about just how precise that is. And be capable of multi-degree of freedom movements. So what's going on in the mechanism of the ant itself that is allowing this multifunctionality and multi-degree of freedom movements? So there's a lot that we have to uncover about this species itself. So it is a very nice circular movement. So if we look at the kinematic data of just the angle versus time, we see that, for about the first 90 degrees of motion, it is pretty much tracking with the circle itself. And afterward, it gets kind of fuzzy, gets kind of weird. And just to further illustrate the point that it is a very nice circular motion, over on the right side is actually 100 strikes over 10 individuals all overlaid on top of each other. And on the left side, we're taking the averages and standard deviations, and we're able to take the velocity and acceleration from this kinematic data, which generally is prone to all of this error amplification because you're doing finite difference methods, and we're still able to pull out the max acceleration and max velocity pretty reliably. So this is a really, really good, nice set of kinematic data, which is really hard to come by in biology. So what we ultimately want to say is, well, what is enabling this, and where is the pin joint that would make that perfectly circular motion? So over on the left side, and this whole slide is an example of what you might find for an arthropod pin joint. And arthropod biomechanics are very different than human biomechanics. So we have pin joints, in our elbow, which allows us that 1 degree of freedom rotation. But the way that an arthropod pin joint is constructed very differently. And so what an arthropod pin joint does is it's actually these two kind of like corncob holders, if you will, depending on where you grew up, that interface with the mechanism and just kind of hold it in place and maybe don't move like a pinch, then a way we think of it in engineering as this bar that goes right through it. So we first asked ourselves, well, where is the pin joint that enables this precise circular motion? So we've got to look through the morphology of the ant itself to try to find this. And so these are some of these very nice colored SEM images of the ant head. And looking through this, we don't find a pin joint. What we find is this kind of weird articulating structure that goes over, and it doesn't look like what we expect. So we have to go back to the drawing board and say, well, what is enabling this circular motion? So even through that dissection, we still don't find that pin joint. But one of the things that we noticed during doing this experiments is that during loading, so the ant is going to load energy into springs, but what it's doing is it not only is pulling on the apodeme itself, but what it's doing is it's storing energy in this chitinous shell that is the head capsule. So if I just move this video, from very quickly from the start to finish, you can see this shape change. So you see the sides of the head bowing in, and you do see a little bit of the head shrinking. And so this is actually another place to store potential energy. And this has allowed us to hypothesize, well, so we find that, this allows us to hypothesize that there is energy storage here in addition to the apodeme, which this energy storage of the chitinous shell, in addition to the apodeme, is really what's contributing to that rotation. But we still haven't solved how does that allow the multi-tool. So when we look at this, and we look at this in this really abstracted kind of way, so we take it from morphology, and then we want to draw the mechanism. So we have our mechanism, which is this mandible interfaced with this kind of curved beam and the muscle and apodeme unit. And what we actually have is that this ends up being, mathematically just two springs in series. And while they don't look like they're in series, they are in series mathematically. And we get these two springs that provide a push and a pull. And eventually what we'll find is that, this is what is responsible for that rotation. So this has helped us solve, well, how are mandibles multi-tools? And so what we have on the left side is in the spring actuated form, and the head capsule is deforming, we get this push from the head capsule and a pull from the apodeme. But during the muscle actuated system, that head capsule is just acting as this simple pivot point. And that simple pivot point is just providing some reaction force to the apodeme being pulled by the muscle, which allows us to have this multi-degree of freedom multi-tool. So this is really interesting to us, and as engineers, we want to define, really rigid kinematics, but we don't see these rigid kinematics. So what are the consequences of having these amorphous joints in trapjaw ants? And so what we do is we take this and we just model a very simple, beam with two springs, and we look at that behavior, and we can ask some of these really fundamental questions. So we can first ask, so we can first model the behavior, and just make a very simple model. And we say, yes, this is how the trap-jaw ant works. It does that. But what we can ask is, what are the consequences if there was a hard pin joint that constrained the motion at that center of rotation? And so we can look at this big design map and we can ask ourselves that question. And so we can vary how is the energy split between those two springs. So right here at the center is a 50-50 split between, head capsule spring and apodeme spring. And more you go to the left, more energy is stored in the head capsule. More you go to the right, more energy is stored in the apodeme. And on this vertical axis is just this lever ratio. So how far apart are those two springs? And right here at this 0.5 energy partition and 90% lever ratio is roughly where the animal exists. And so we find that, there's a few consequences we have when we put in this hard constrained pin joint. One, we get these behaviors where we don't actually get mandible closure, so we get this oscillatory behavior. And two, we find that we are not at a maximum power. So that makes us scratch our heads and we wonder why we're not at a maximum power. Why isn't everything not optimized for power? So we can compare that to, well, what if we let this have this amorphous joint? So this allows for both translation and rotation, and there's no hard constrained pin joint at that center of rotation. And so again, where that crosshairs is where the animal exists. And when we allow this translation, we no longer have that oscillatory behavior, and this power map looks a little bit different, but we're still not at a maximum power. And, well, what is the difference between these two maps? And what do we actually see? So if we actually subtract one map from the other and take the log of that difference, so then, anything that is not different between those two maps shows up as this white strip in the center, then we get an idea of how these systems are different. And so what we ultimately find is that to get a purely circular rotation, we need this equal energy partition, which just provides a moment couple without translation. And this is what enables the trap-jaw ant to have that perfectly circular motion, all without a hard kinematic constraint. So this amorphous pin joint inside the trap-jaw ant is really just a result of the dynamics itself of the mechanism. And so, we can even look at this in the same way in some of these systems, and we can get the same behavior when we have, pin joint or no pin joint, but the same energy. And when we take the energy and we split it unequally, then we get some of these weird behaviors that don't exist in nature. And so, we get some of that reloading of the head capsule on this right-hand side when we do have a really hard pin joint constraint, which would really mess up the mechanism itself. And so this has allowed us to, tease apart the mechanism within the morphology of the ant, and upon reflection, just coming to the fact that, oh, this is just a way to make a purely torque-driven behavior, or the pure moment couple without translation. It seemed very obvious in hindsight, but it took us a while to actually piece all of these things together, from biology to math to mechanics, and really understand what is going on in this system. And we're even able to look at this in the context of engineering, and we see that there's this inherent trade-off between high-speed motion, highly precise motion, and high range of motion. And so, as a comparison, this is a micro robot that I made a few years back, and it's 1 millimeter, it's 2 millimeters long, and you see that the legs are wobbling a lot. So I can get very highly, I can get very fast circular motion in the legs, but it's not very precise. And I do get a very high range of motion because it's able to complete multiple turns. And for comparison, this is a MEMS rotary actuator. And what we're able to do here is we can get very precise circular motion with high range of motion, but we're ultimately limited by surface forces, which will restrict the speeds of these devices. And so this has really given us a lot of idea about, well, what is going on with this dual spring actuation in terms of arthropod joints. And one, this adds a new type of joint that has not previously been defined in the arthropod literature, and we believe is a we believe it's pretty unique. We believe that it's not just unique to the trapjaw ant, but all of other high acceleration systems are using this, such as the mantis shrimp and the snapping shrimp. But we've been doing some investigative work in order to figure that out. But this also has a huge consequence for multifunctional robotics and MEMS. So if we can make these systems that can switch between these high impulsive behaviors and also these directly actuated behaviors, then we can make these really multifunctional robots. And so those are some of these driving questions that are enabling new lines of research in my own lab. And I really just wanted to kind of take this as a fundamental takeaway of what I'm looking at in my lab. So I really want to make the distinction that I'm not just doing, biomimetic robotics, but I'm trying to use robots to understand, the fundamental rules for designing and control of robots. And we're not just copying morphology, but we're trying to learn, what are these inherent trade-offs. And with that, I think we can have time for any questions or discussion, especially if you wanted more insect fun facts.
Thanks, Ryan, for that fascinating talk. Yeah, so we are open to discussion and questions. This is very unique stuff. You can unmute yourself and ask questions as they come to you.
It's really exciting work. I put a couple of questions if I could. So,
yeah.
Thank you, Ryan. This is Subbu Ramakrishnan, University of Minnesota, Duluth campus. We've been interested in ants for a while now, mostly from the point of view of collective behavior. But we've also tried to, model some soft robotic arms recently. So this work, your work is very interesting to me. So first question. All this is happening in the plane, right? I mean, do you even consider R3, or from the standpoint of ants, is it not relevant? I mean, because all the motion is in the plane?
Yeah, so what's really interesting here, especially about the trapjaw ant, is so the way it's obviously pretty small. I have that 1 millimeter scale bar, and it's pretty high speed motion. And so the depth of fields on this system with these optics is really, really shallow. And so the mandibles themselves are moving in plane almost the entire time until it reaches this 90-degree angle. And so past 90 degrees, the mandibles cross over each other, and then you get out of plane motion.
Okay.
And so, if we would not have been able to image this had the trapjaw ant motion not been in plane at all, we wouldn't have been able to image both mandibles at the same time.
Okay.
So
Thank you.
After the 90 degree is really when you get that really amorphous joint takeover and those mandibles just cross and do whatever. It's a particularly underdamped system after then, which is also really interesting.
Right. And all of this is happening with a central nervous system, right? I'm asking because there's a lot of interest in this morphological computation recently, where when things have distributed computing rather than a central system, right? But I suppose these ants are still operating, I mean, at least as far as we know, still with a central control, I mean, centralized.
Yeah, so they have ganglia, which is just the cluster of nerves that is their brain. They do have trigger hairs close to their mouth, which when those are triggered, that's what sends the impulse to close the mandibles. I don't know if those trigger hairs are directly tied to a latch release mechanism or if it goes through the brain itself.
Okay.
As a counterpoint, the Venus flytrap, which operates under these same set of dynamics, do also have trigger hairs. And they are just providing this chemical release. And they clearly don't have a brain. So there is some sort of pathway, but it's not purely mechanically mediated, but there are other systems that are pretty mechanically mediated in how they kind of snap.
I see.
I'm not sure too much about insect neurology. I am mostly a mechanical engineer still.
Yeah, no, I'm in mechanical engineering myself, but that's quite useful. Thank you. And final point is not a question, but more of an observation. So recently we've tried out a particular nonlinear oscillator model coupling the translational degree of freedom to the rotational degree of freedom from the standpoint of soft robotics. And a student was able to show, that controlled circular motion would be possible with that nonlinear model. And in some sense, when he showed the morphology of those ants, it gets me very excited because it's very reminiscent of what we try to capture. But on that note, I probably would like to reach out to you, soon to talk about that sometime.
Yeah, I would love to talk about that.
Yeah, thank you.
I think some flowers have this kind of behavior also, right, Ryan?
So plant movement is something else that I'm just particularly fascinated by, because you get plants that either move through mechanical instability. So you like the Venus flytrap, which has that bistable structure that snaps through, or it's just through pumping fluid. And so in the pumping fluid case, you're limited in time scale by how fast you can pump fluid, versus the mechanical instability, you're just limited by the materials and mechanism itself. And so to make some of those jumps in time scale, you do have to employ these mechanical structures and that mechanical computing.
So the time scales are different. You can't get to these speeds.
You can't get to those speeds with just pressure. There's a lot of seed dispersal mechanisms that do rely on this as well, where they have these catapult mechanisms that explode and just fling seeds everywhere.
So it has evolutionary implications.
Yeah. This behavior has evolved multiple times over many different kinds of creatures, plants, arthropods, frogs exhibit some of these things. So it's across kingdoms, and you even see it as a way for. So one of the other structures are stinging cells in jellyfish, which are they're just cells that build up pressure and squeeze out a little harpoon. And the reason why that evolved was to actually be able to move that little harpoon in a particularly viscous low Reynolds number environment. So it needed that really high burst of acceleration first in order to overcome these low Reynolds limits and actually pierce a boundary layer and pierce its prey item. I think you're muted, or I have lost audio.
Yeah, I think Surjit is muted. Surjit, you're muted.
I am muted. Thank you. Thank you for pointing it out. This is the umpteenth time that has happened. So Sumana has asked a question, and you can unmute and ask yourself, Sumana, but I'll ask it for you for now. Is there a relationship between the ambient temperature and movement of the mandible, particularly the speed achieved?
That is a great question.
Yeah.
So one of the hypotheses that we have that these spring actuated systems, evolved was to be thermally robust. And you can, the muscle itself may work slower in a colder environment, but it's still going to load up the energy into the spring, and the mandible itself will move based upon the spring recoil. And so this has allowed, our hypothesis about this is actually in relation to chameleons and salamanders. And they are still able to do that ballistic behavior of their tongue through a diversity of temperatures. So they're still loading up these elastic materials and then still firing their tongue at the same rate, because that is all mechanically mediated and mechanically controlled. So these spring actuated mechanisms allow for a degree of thermal robustness and allow for biological creatures to work in a variety of environments. And as engineers, having these mechanical controls and these mechanical components, I've always described this as, it's a way for me to overcome the limitations of the shitty actuators that I buy from Amazon. So they don't all work the same, but if I can put a little mechanical control in between the actuator and the robot, then I can get them all to work relatively the same and do this idea of filtering through mechanical structures.
I got a question here.
Yeah, Shidang, please.
Yeah, so near the beginning, you were sort of measuring the velocity of those mandibles.
Mhm.
And you talked about the dependence on the L, the size of the mandible. From a operational perspective for the ants, wouldn't it be the momentum that is the most important? Like they want the impact, right?
Yeah, so these they're different strikes, if you will. And so I think some of them do puncture. And so that is a little bit more about, momentum and geometry and material.
Mhm.
And then the other thing is there is a scaling effect under which spring actuated systems would work better, if you will. They have higher velocities, higher accelerations than muscle actuated systems. And so depending on how you are considering some of those trade-offs, then you would get these high accelerations that you would not be able to get with muscle alone. And I think that, if it is particularly, I'm not really sure, and I don't really know the phylogeny of all of the different trapjaw ants, but they do all have very, very different mandibles. Some are longer, some are shorter. And I think that they may be more specialized to prey items and inflicting damage to certain items.
I'm not sure I said it clearly. I'm talking about momentum versus velocity, not acceleration. Right?
So I think there is trade-offs between, are we optimizing for momentum or are we optimizing for velocity?
Right, exactly.
And I don't know which ants are optimizing for which, metric.
Okay.
But I do know that there's a diversity of mandible geometry and size among the phylogeny of trapjaw ants. I think it would be really interesting to look at that with respect to where they live, their ecology, and what they hunt. So
you really use it for
what they use it for. And I think, maybe if they hunt particularly soft-bodied things, maybe they have to impart more momentum per strike. that's just a hypothesis. I think the other thing is, you know, a lot of these considerations when we look at biology, we can't just look at the mechanism alone. We have to consider their evolution and ecology as well.
Mhm. Okay, thank you.
Sunny, you had a question? Sunny, go ahead.
Yeah, I have a question, Ryan. That was very, very nice talk. Yeah. Speaking of scaling law, and what is the maximum size of this multi-tools in your mind based on ants' behavior we can design or think of?
Yeah, so I think that with the ant itself, of the ant, so the apodeme and the chitin, I think that there's going to be a maximum of a mandible size, you know, maybe a few millimeters. But what I always like to point out for robots is we're not limited by evolutionary history. So robots can always be incarnated in a new system with new materials, new mechanisms, whereas evolution always comes from something before. So if we can make springs that store way, 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 way more energy in a system, so if we need to make them nonlinear in some way, or you know, these metamaterial springs that allow for more energy storage, then we can make things bigger. And so there's a lot of these engineering tricks that we can play to kind of, you know, skirt the laws of physics, if you will.
Thank you. So talking about this, so we can make some compromises such that we can increase the size.
Yeah.
Without losing this scaling law effect.
Yeah, I think that, you know, the main thing that I always want to impress upon, you know, when I give these talks, it's all about trade-offs. What are you giving up and what are you taking on? You can't have it all.
Thank you.
What about the mandible shapes? I mean, I was just wondering that you probably can have mandibles with all kinds of shapes and all kinds of weaponry in the leading end, right? In the striking end. Is there much diversity that you see in the animal world, in the ant world? And
yeah, there's a ton of diversity. Some are very like long and slender, which may, you know, be much more compliant upon impact. And maybe that compliance on impact allows you to do this sort of double strike, if you will, where you're hitting once here and then the tip hits again. Some mandibles are shorter and more stubby. Some are modified for cutting vegetation. So there really is a diversity of mandibles and a diversity of striking behaviors that, you know, I find fascinating, because it's a tool that's evolved multiple times over a bunch of different animals, and they all use them in really different ways.
It's very non-universal as a tool.
Yeah.
For function. The mechanism is fairly universal, but the tool itself seems fundamentally quite non-universal.
Yeah.
That's fascinating.
Yeah, you've got to really take into account what they do with that.
I mean, I was thinking about something that this was quite a few years ago, about 15 years ago. There was a lot of talk about how robots function on the surface of Mars, for example, how they are to be designed, because this is an unknown surface, right? You have rocks, you have sand, you have all kinds of stuff. And the rock structures can be quite different. It can be rough rock, smooth rock. And it fascinates me to think that potentially not two, but one of these structures can be very useful for climbing, right? Because you can literally catapult yourself. And I was just curious whether that has been used as an evolutionary apparatus for for climbing in the animal world.
I don't know of anything that climbs with this mechanism off the top of my head. But I think that, these engineering multifunctional tools that can either do, striking to like stick to a rock and then launch itself off, or could use it to just climb, that would be awesome. I would love to
Yeah,
do
because
that.
if you can do in series, right? If you can make it into a, if you can make it into a hopper,
Mhm.
Yeah, that could fundamentally be useful for planetary scale geology and all kinds of applications.
Yeah.
We should talk about that. Wow. Other questions? Are you sure you don't have no other questions?
It's nearly noon, so I think people are hungry.
That is true. It's no time. Yeah. All right. If there are no further questions, let's thank Ryan for a really fun morning, evening, night for those of you in other parts of the world. This is really nice, and if you want to connect with Ryan individually, like Subbu wanted to, please feel free to do so. It'll be, I'm sure he'll appreciate that. He's setting up his lab. We are also thinking of some other problems, and hopefully we'll talk about that down the road. Thank you, and bye-bye, and have a great weekend.
Thank you.
And thanks, Ryan.
Thanks. Bye.
Thank you.